All right, so we're going to look at a different type of special limit, but before that we do that, we need to talk about slope. Because this limit actually helps us find the instantaneous rate of change or the instantaneous slope. And what that means is if I have a crooked number line, crooked coordinate plane, there we go, and let's say that I have a function on here like this. Here's my function. When I find slope, I take 2 points and I find the slope in between those 2 points, like that. And our slope formula was m equals y sub 2 minus y sub 1 all over x sub 2 minus x sub 1, because I have 2 points. Well, in calculus we actually would write that different. We would write f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. So in calculus I write it a little bit different. Now this is what we call average slope. What I want to know is the instantaneous slope. I want to find the slope right here, and what that means is I want the difference between this x value, x sub 1, and x sub 2, I want that to go down to 0. And so the difference between these in calculus, we call the difference between those delta x. So the change between these, we want these two to have no space in between them. So we're going to take the limit as the change in the x goes all the way to 0. And when the change in x is all the way at 0, then I'm at a point right here, which is called instantaneous rate of change, or instantaneous slope. Now the problem is I can't just subtract these two values. So what happens, this y sub 1 is what we have, just our function, our f of x sub 1 if you wanted, but it's just f of x. The other y value, so you have your x and your y value. The other y value, what we call it is, it's actually the y value evaluated at the first x plus the change from here to here. So the change from here to here is delta x. That's not looking right. Let's try that again. Delta x. So this means the function evaluated at the change between these two x values minus the function at this value, because that's what we did, we're subtracting, that's the change in the y's, over the change in the x, how much the x changes, and we want that change to go to 0. So how are we going to do that? Well, they'll give you a function. You're going to use this and you're going to try to find the instantaneous slope. So let's say that I have the function, let's do a linear function, 2x plus 4. And I want to know the instantaneous slope using this formula. Or I want to take the limit as the change in x goes to 0. So I take the limit as the change in x approaches 0 of my function, this is my function, evaluated at x plus delta x. That means x plus delta x has to go in for x. So it's going to be 2 times x plus delta x plus 4. So I just put in x plus delta x for x minus, now this is the original function. So the original function goes here. My function is 2x plus 4. Now I use parentheses again because we're going to have to distribute the negative. And it's all over the change of x. So this is just a really complicated way to say y2, this is my y value, minus my other y value. And now you're going to do some algebra because you can't just plug 0 in because it's not going to work. So I have to do algebra like we've been practicing. So I get 2x plus 2 delta x plus 4 minus 2x minus 4 all over delta x. I'm going to keep going simplifying. I see that I have a 2 and a negative 2 and a 4 and a negative 4, so those all cancel. So the limit as delta x approaches 0, I now have 2 delta x over delta x, which means delta x over delta x, I can cancel those. So I have the limit as delta x approaches 0 of 2. Well, the limit of a constant is just that constant, so the answer is 2. That is the instantaneous slope at any point. So what we're really doing is we're not quite ready to say any more about the slope, but what we are ready to do is to evaluate the limit. So let me show you a little bit different one. How about the limit as delta x approaches 0 of, how about, of f of x plus delta x minus f of x, because this is our formula. Just think of it as a formula, as a slope formula of delta x. And let's say that our function this time is a square root function. How about the square root of x? We'll just use that. So how can I do that? Well, I'm going to take the limit as delta x approaches 0 of my function evaluated here. So that means x plus delta x has to go inside for x. So the square root of x plus delta x minus the original function, that's my original y value, so square root of x, so this and this are going to be the same, all over delta x. So I can try to just plug in 0, but I can already tell it's not going to work. And now I see square roots, so I'm going to think that I'm going to use my conjugate. So I get x plus delta x plus the square root of x, and then on the bottom I get the same thing. And now I'm going to multiply everything. And my numerator, when I multiply, I get x plus delta x minus x all over delta x times the quantity of the square root of x plus delta x plus the square root of x. Now, hopefully you see why I was acting shocked that in the numerator these were going to cancel. So now I have just delta x over delta x times the square root of x plus delta x plus the square root of x. And it's similar to the problems we've done before. These two, now that this one's being multiplied, we can cancel. So I get 1 over the square root of x plus delta x plus the square root of x. And I'm taking the limit as delta x approaches 0. So now I'm going to plug 0 in here. So I get 1 over the square root of x plus the square root of x, which is 1 over 2 square root of x, which seems weird for us because we've been getting number values. And the reason that this one is not a number value is because basically you just found a slope formula. This is a slope formula to find the instantaneous rate of change anywhere that I want on that point. But for right now, just realize that when you're doing these delta x ones, you might not always get a just constant. You might get another function, a new function. This new function, actually, it's called the derivative. So I've used that word for us before, but that's actually the derivative of that. All right, so now you have a few of these to try. Remember your rules, conjugates, factoring, common denominators when you're doing these. Have a good day.